Okay, so thank you very much. I should also actually thank Arthur for inviting me, and of course also Renata, the other organizer, and the other organizers. So I know Arthur from many years back, and when he asked me to speak at this conference, he told me that it will be here, I want to come, and now I'm glad I'm here, but I don't see Arthur. I hope, Arthur, you hear me and you see me.
I can hear you and I can see you. It's
okay,
great.
good.
Thank you for coming.
I was also thinking actually what I should present here because I may be a second exception of the rule of the Misha. So maybe it's a good bracket for the day-to-day, which means Misha starting with physics, more on the physics side, and me finishing also more on the physics side. So I decided to talk about something where I actually could also show some link to Arthur, and we did some work a few years back. I should acknowledge my collaborators here. Okay, so the outline of my talk is I give a brief motivation and then say something about the spin ladders, majoranas in there, and the main part of my talk will then be on fractional spin phases in conduct necklace spin ladders and spin transport. So the motivation for us, and I think for many in this field, more on the physics side, is to find physical platforms where we can implement ideas for topological quantum computing. And for some people, this is just an engineering question, but for some of us, for physicists, it's actually highly non-trivial to find systems which really can implement it in a realistic setting. And very often, very harmless looking requirements can make it completely unrealistic to have physics experiments on it. So typical candidate systems actually, which have made a lot of progress and impression in the field, they're usually based on charge carriers, electronic systems, which people have tried to use as a platform and to show fractional statistics, anion behavior, and so forth. And the best, the most studied system are actually topological insulators, and in particular nanowires, where claims have been made to observe such objects like majorana. But you know, as many of you probably know, there is a little bit of a crisis here. One can call it the majorana crisis. It has turned out that the number of experiments did not really hold up to scrutiny. Nevertheless, a typical setup in such experiments is shown here. And this is from a paper which has been retracted, but the device is still valid. There's nothing wrong about this device. And I think you know, people are still trying to find out why this device, for example, shows features like this. And the big question in the field is a zero bias peak in such a plot here, this line, is that a majorana or not? And it's not a label which says I'm a majorana. You really have to find out whether it behaves like that. And it turned out that features like this are most likely actually what we call now trivial states or Andreev-bound states. And there are many issues in setups like this here, like the spin-orbit interaction, which is a very important ingredient, the proximity effect by superconductivity to induce a gap and disorder and so forth. And so this might actually beg the question, should we reconsider platforms, go to other platforms? And of course, there are many platforms which have been proposed in this business, and some of them are based on spins. And this is something I would like now to go back a little bit, because we think there's quite some potential also in these spins, given now the current situation in electronic systems. So let me introduce here a simple model, which is actually not that far from experimental realization, but also not that close. You will see in a moment why. So this is a spin ladder, and we have here these red, green, red, blue links, and they all have a different exchange interaction. So here's a spin exchange Hamiltonian, which is icing-like. So along this axis here, it is Y-Y interaction, then here X-X, and the blue one is Z-Z. This is kind of a quasi one-dimensional version of the so-called compass or honeycomb model which has a long history, but has been worked also by Kitaev to look for Majorana like excitations in the system. And how do you proceed to see Majoranas in this system? It's actually rather simple. You represent the spin algebra, the Pauli spin operators by the Dirac representation. This is what Dirac introduced many years ago in terms of gamma matrices, and if they are in a real format, then you just call them Majoranas. And these Majoranas, they anti-commute have typical fermionic statistics, but are real quantities, self-Hermitian. And this representation allows them to rewrite this Hamiltonian as a Hamiltonian of quartic terms in Majoranas, and it turns out that these inner products, they just square up to 1, eigenvalues, then plus minus 1, and you end up with a quadratic Hamiltonian in Majoranas. And this is owed then to the special Ising-like structure here. And these kind of eigenvalues here, they label your Hilbert space, and one can also interpret that physically as a vortex, which basically describes when you go around the plaquette, that you have a +1 or a -1. And there are many possibilities now of high multiplicity. And basically, this is still an unphysical extension of the original Hamiltonian because of this mapping here. And when you map it back, you have to project it. And this on the physical state. And this begs then the question, what kind of structure, of vortex structure we have in such a wire. One can then see that solving this equation, it's quadratic, this Hamiltonian, you get the spectrum and you find indeed Majoranas, and these Majoranas are located, let's say, in the inhomogeneous ladder at the end and at the interface between a topological phase, so that you can characterize this by a topological number, by a trivial phase, and this you just change by tuning the coupling constant. Here, for example, the JZ coupling constant is larger than the other two, the X and the Y. Whereas here it is smaller, and then you're on the topological phase, and here you're on the non-topological phase, and here again, let's say the topological phase. This topological phase is not completely stable. I mean, it's symmetry, protected topology. If this symmetry is not given, then it's not so difficult to destroy this phase, for example, with two-body type of interactions. But it's rather robust, this entire system, against single particle or magnetic field, for example. And one can think of such a system to build networks and have tri-junctions such that even braiding of these Majoranas in this system is possible, and conceptually rather simple, basically by changing the exchange interaction, for example, with electric means, you can shift then the Majoranas as been proposed in electronic systems. You can do similar things in this system. What is not completely obvious is, are these states are also non-abelian, and as a matter of fact, this goes back to this vortex structure which is induced in this mapping, and there might actually be vortices in between, and then when you go through them, parity of your particles can change. So then we discussed this also with Arthur, whether actually it would be possible to prove what the ground state looks like. And Arthur came up then with this very nice idea of using reflection symmetry and so-called reflection positivity. Probably most of you, I think, working in the mathematical world are more familiar with this. And basically, the reflection symmetry is an obvious symmetry you can ask. So, for example, you can take a vertical line and then reflect around this line, and you would like to have everything preserved, and you call it reflection symmetric around this plane, or you can also look at this here. And given this reflection symmetry of the system or of the Hamiltonian, and mapping this, as I shown before, to Majoranas, Arthur and one of my students, they could actually show that the ground state satisfies so-called reflection positivity, as is defined here. And given this reflection positivity, it was then possible to show this following theorem, theorem 2 in this paper, namely that given reflection symmetry, then the ground state of such a spin ladder is vortex free. And that's very good news. Basically, it means indeed one can use this as a starting point to consider majoranas and do braiding in this system. We also found that this high symmetry is not even needed. We were not able actually to prove that it still holds the theorem, but rigorously, but using perturbation expansion, for example, in the coupling constant, and also doing numerics, we found that the statement of the theorem still applies, even if the symmetry actually is not given. It's also quite interesting. So that's from a rigorous point of view, is still an open question. And systems like this might be implemented in atoms and surfaces. I will show a few experimental examples later, but listening to the talk this morning of our chairman, maybe that's a system which Rydberg atoms could also easily do. So it's the minimal system of getting a majorana in a spin system, which is braidable. Okay, good. Then in the next part of my talk, I would like to talk about some more recent work where we looked at so-called spiral Heisenberg spin ladders, which also have very interesting properties, especially taking into account now strong interactions. So what is the system? So there are kind of two extreme cases. So we have one spin chain here, A chain, and the B chain here, second one, and exchange interaction of short and long range, can be more than second nearest neighbor, third nearest neighbor, let's say, and the same in this B chain. And we have coupling between the two chains here with J perp, which we consider as a perturbation, and we will then do perturbation expansion later in this quantity. And we apply in addition a magnetic field to control the magnetization in this system. One can view now such a two-chain system as a so-called spiral staircase Heisenberg ladder. If you take now one chain and take the other chain and kind of twist it around it, and if you do that, you get a shape like this here, where you can twist around. So seen then from the top, you have an angle theta. So this case here corresponds to theta equals 0. So isotropic Heisenberg ladder, and another one, if theta is pi, carries the name of a condo necklace model. It's actually a model which goes back very much in time to Domjach, looking at some condo model, but now it's also used for this system. And there are some experimental compounds which are claimed to come close to this system. So to see how to get to this, for example, you can think of a ladder like here, and then every second atom, you take a different one, and then you flip it, and you get then this kind of necklace, condo necklace. So here's this compound. I will not go into more detail, but some people have claimed that it comes close to this. And in addition now, you also add some long-range exchange interaction in this model. We will see in a moment why we need that. Okay, so here, just to show that building atomistic spin ladders is not completely science fiction anymore. So here is a collection of what people do in various systems. So these are atoms on surfaces. For example, here iron atoms on the surface of platinum, or cobalt chain on platinum, zigzag chains and so forth, or iron and potassium and so forth. Or for example, here in Ari Yastani's lab, now one can study then the dependence when you grow these chains on the orientation, the distance also between the atoms and so forth. So there's a lot of kind of tunability available. Here's another one in Stuart Parkin's lab, where they also can build chains of different orientations on substrates, which gives them also different exchange coupling. So just as a motivation that is not completely science fiction, as I say, but I think for Rydberg atoms, it would be very nice, because Rydberg atoms have long range interaction. That's something which we will see now is a very important ingredient. So here's the Hamiltonian written down again for one chain here and for the second chain, and in the presence of a Zeeman field, like this here, and this is the interchain coupling between the A and the B chain. So how do we analyze this system? So there are several steps. First, we fermionize. It's a spin 1/2 chain. We do this by Jordan-Wigner transformation. That's standard. But as soon as you go out of one dimension, it becomes more complex because there's a string attached, and the string operator to deal with that in higher dimensions is rather tedious. But we will see that for the purpose we have in mind, it does actually not really bother us. So after fermionizing, we can look then at the spectrum without the Z-Z interaction. So there's just a standard fermionic dispersion. And the magnetization basically plays the role of a chemical potential and defines then a Fermi momentum, as is indicated here. So with the magnetic field, we can tune the system. We can tune the filling, so to speak, of that chain. And the magnetization can be tuned by the magnetic field. So we have an external parameter to handle that system. And this magnetization per side and is uniform, does not depend on the side. And it's also important to emphasize that the total spin in each chain separately can be conserved. And then in a further step, we go back to another representation, we bosonize the fermions, express them in terms of this exponential, because each chain is one-dimensional and can do that. And we have then bosonic fields satisfying standard bosonic commutation relation. So the shut up is the conclusion is then that the spin chain can be represented in terms of a latential liquid system with parameters K, latential liquid parameters for the chain A and B, which are dependent on the original exchange coupling constants. I will show in a second how. And if K is very small, then we call this strong interactions in the system. And if it approaches free in the system, then this case are 1. So for example, it's very well known, if you spin 1/2 chain and you bosonize it in the same way here, then you can actually find the Bethe-Ansatz solution of the problem, which gives you an exact relation between this latential liquid parameter K and the original exchange couplings in the Hamiltonian. And there is a phase where we call this phase latential liquid phase, already introduced by Halde many years ago. And this just shows that we can essentially control this K. However, in the presence of a magnetic field, and this is what we want because we need this as a control parameter, Bethe-Ansatz does not work. And we need to find then this K in a different way. And this we do now here in our work, just using standard DMRG, density matrix renormalization group methods, numerical methods. You look at the correlation function of the spin, and depending then on the magnetization, the chemical potential, you can find then K depending on the original coefficients J and X. So for example, here is a plot as K as a function of M, for example, for the value as indicated here. So also here, the conclusion is that this parameter K can be tuned via magnetic field because magnetic field tunes the magnetization. Good. And now let's go further and add the interchain interaction, which we treat, as I said, as a perturbation. And in the fermionic representation, so we take here now the lowest order, which gives us a non-trivial term. And such terms are of this shape here. So they are powers of left and right goers. And these powers, these terms we can interpret in the fermionic language as backscattering terms. So the fermions get backscattered and pick up because in the fermionic language they have oscillatory Fermi phases, this overall phase. And now these terms become relevant in terms of as a perturbation if this phase factor here approaches 1. And this gives us a constraint on these powers S here and connecting the Fermi momentum or in terms of magnetization. And this is the constraint which we deduced from this. This means if this is satisfied, terms like this are important. And we keep these terms, these interacting terms. And now, bosonizing this term, we get a very simple looking effective Hamiltonian, which is just a harmonic function of the fields phi tau of A and B. So we have these bosonized fields and some power here in the coupling constant. And these terms we can analyze now using standard renormalization group treatment, and they turn out to be relevant if the so-called scaling dimension of this operator here is smaller than 1. And with these numbers in here and the S tau and the K in the free action, we get this condition. And that means if this condition is satisfied, this term here will create a new phase and can open a gap. It will not open a full gap in general because not all fields are involved. It will, one can also tune the system, but that will be fine tuning. In general, it will open then a fractional, a partial gap. And the statement now is in this phase, in this new phase, we can calculate the spin excitation and find that the spin excitation can be expressed in terms of these powers here as A and as B, namely as this fraction here. In general, this gives us then a fractional spin. And so that means we have now found a new phase of matter with all excitations carrying fractional spin to begin with. The question now is, we made a few assumptions on these original parameters of the system. So what kind of values of exchange actually are allowed. And it turns out that we need very strong interaction in order to get these constants, these Luttinger liquid parameters below this limit, so that we can satisfy this. These numbers S are typically on the order 1. So definitely we need that this here is smaller than 1/2. And this is indeed actually reachable. So doing this DMRG calculation, as indicated before, one can show now that when I increase the long range coupling constant, then this Luttinger liquid parameter indeed goes down to a value which we would like to have. So here's an example of such numbers which work. That so here we get the backscattering, let's say a square here, a 1, and this scaling dimension has to satisfy this here, and this means that one of these Luttinger liquid parameters has to be smaller than 0.375, and this is indeed reachable if the magnetization can be tuned or is tuned by the magnetic field. And so that means this system should be within reach. So the big requirement is to have interactions between spins which are longer than just the nearest neighbor. We also confirmed this fractional spin phase fully from scratch using numerically using DMRG again, and found actually a new quantity which is very useful to characterize this new phase. Basically a generalization of electric polarization, a magnetic dipole moment. So you take the magnetization of each chain and multiply it by the side and take the sum over it. And this quantity allows us then to identify the ground state, or the basically the magnetic dipole moment gives then differences of the ground state. The ground state, as soon as we have such excitations, is actually degenerate, n-fold degenerate, and we can look then, for example, here's an example between two different such ground states, which are equal in energy, but characterized by different quantum numbers. And then this polarization can be calculated in there. One can show analytically that this difference is directly giving actually these fractional spin excitations. And so this here can be calculated now numerically. So here's an example of this. We have this, again, this resonance condition. This defines this line in the plot here of magnetization B versus MA. And on this line here, one can check then numerically that all these squares, they satisfy that this number here indeed is 1/3, as we know from the previous RG analysis. So here's, for example, a numerical calculation how this polarization difference reaches its asymptotic value of 1/3 if one increases the exchange interaction. But this gives us a very strong confidence that indeed this phase exists. We have found now several methods this. So how can one observe it? Some of it turns up in the dynamical spin structure factor defined here. One can look then at the spectrum essentially and find the gap in the system where these quantum numbers appear. But unfortunately, they're still kind of convoluted with non-universal values, so it's difficult from such a measurement. At least one would see the gap, but it's difficult to see the fractional excitations. There are other ways to access the fractional excitations, and this is by spin transport. Given now a little bit my time, I should probably rush. It's possible to measure spin currents in the same way as charge currents. This opens up actually a very rich kind of playground. As a matter of fact, also here in Harvard, it was Amir Jacobi's work which showed that one can generate artificially a chemical potential for bosons, for magnons. And this is basically creating a battery of magnons which can drive a magnon current. Or if you have other spin excitations, a spin current. So that's also something which we know from experiments, and people have thought about attaching leads in order to basically have chains or other structures to drive currents through that. And this is something which we have looked at many years ago and shown that then the conductance of such a spin current is, let's say for an antiferromagnet, is quantized. Now, not in units of E²/h as it is for an electric system, but in G mu Bohr (²/h). This is the elementary unit. So yeah, like this. And now we can also consider this for these spin ladders, for this helical or this spiral spin ladder, and calculate this conductance, and just quickly show the result here now. That indeed one gets a very nice expression expressed now in terms of these numbers which occur in the fractional spin. It's actually the ratio of these two numbers, SA/SB. And it's so that means measuring the conductance, we can deduce in principle this quantity, and the same ratio also appears in this constraint, which can also be measured independently. So there are two ways, and this will eventually give then the fractional number here. And here again, this universal value appears if the reservoir basically are isolated single chains. Okay, so here quickly an example. If the spin is 1/3, spin conductance would then have this universal number 1/10 in this case. And these are the conditions again on the chain, and then can go through the same exercise and indeed show then in the end that this regime is in principle reachable. So I'm just talking now to my chairman. I hope he listened. It's published. And this brings me to the conclusions. So I have talked a little bit about physical platforms, how to look for excitations, exotic excitations, which carry majoranas and other exotic excitations. We still don't know what the braiding statistics is in these ladders, but we are working on it. And there are also ideas how to extend this now from quasi 1D to 2D, basically by a coupled wire construction that also seems to be possible. And we think that in the end, we'll get really the extended system with these very exotic phases. Okay, so with this, thank you very much. This mass
would they be actually topological? Or because that's my worry is that often sense of
yeah, actually that's a very good question. I briefly alluded to it. I mean, if you have a single chain and
could you repeat the question? I could not hear the question.
Okay, so the question of Misha looking was, can one actually use these majoranas in the spin ladders, let's say for topological protection? Now, for topological protection, I think yes, to some extent, but for braiding, that's another issue, because the Jordan-Wegener string will make the object actually non-local. So one of the majoranas you can always choose in such a way that one of the end majoranas will be local, but the other one will have a string attached to it. And when you move them around or braid them, then you have to deal with that string. And actually with Jaroslav Tsakovniak, we have a paper where we showed that for one-dimensional chains, it doesn't work. Now it's different here for the ladder, for the inhomogeneous ladder. This is actually the nice thing, because there we don't use this Jordan-Wegener transformation. We use this Dirac mapping, and the mapping to begin with is only local. And the non-locality could come in via the vortices, because there could be vortices in between. And then when you link, then it could also connect. But with the theorem, which we have proven with Arthur, that in the ground state, there are no vortices in there. This we know. And one can also show actually numerically, for example, that adding a vortex costs you energy. And this is only true for open chains. If you have closed chains with periodic boundary conditions, then there's a degeneracy and you can have vortices in there, and it doesn't matter actually where they are placed. So, but this is only true for the inhomogeneous chain. If you have a homogeneous system, like let's say the extended honeycomb model of Kitaev, then this would not work. So it's very special. And yes, I mean, if you can control the interactions, then I think it's possible to use this for topological purposes. Okay.
So what about this braiding? What braiding potentially could be the best way to potentially absorb it. So what is, do you have ideas?
Yeah, well, I mean, it's you know, I just go back to this picture. So here, this is key. So it's a kind of a tri-junction. So you have one ladder here and a connected ladder here. And you have exchange coupling like this here. And now you basically control the exchange in Z here, here, here. You just make it smaller. And then the majorana, which is located here, will move. Then you can go around the corner and move it down or move it over, and the same is here. So changing adiabatically these exchange couplings. So for example, I could think of quantum dots, coupled quantum dots to my N array, which would allow me to change the exchange interaction. What is not so trivial is to get a exchange interaction which is highly anisotropic, so it should be icing-like. I think it's possible in certain systems with strong spin-order interaction. I think with maybe with atoms it's even easier to do that. Okay, so this is a very good question. I think with this model, probably not, but with the other model, here I'm pretty sure, yes. Because you know, the majorana doesn't really need much interactions. But in this model, we have very strong interactions which we can exploit. And this is exactly actually where we are driving at. And my guess is, yes, it should be possible. And it should be possible, okay, I would speculate maybe even beyond parafermions. But it's a way to construct now. This is actually what we like very much about this game now. Now we have some kind of a recipe how to construct the systems which we would like to have, and they are not completely far away from implementing.
Yeah, I have a question which goes back to the beginning of your talk. That's because how do you prove that something is a majorana or not? I mean, it would just be fantastic if you could have any hint, because I was trying to think of what I would do. I don't know.
I think, you know, I would say probably most people would say the simplest way to prove it is to do braiding. You know, if you then look whether we have non-abelian properties, right? But that is already very far out. And I don't know if you want to invest so much on your system until you could do the braiding and not having some confirmation that you're on the right path already before. And this is a very difficult question now. In the beginning, 10 years ago, you know, it meant, okay, there's one prediction, namely that the majorana sits at zero energy in the system. So you go measure, if you see a signal at zero energy, that's it. And if someone would say, okay, could it be anything else? No one had an answer. And therefore, it was kind of okay to conclude it might be a majorana. But later it turned out, or actually not that long later. I mean, already 10 years ago, people knew that when you add this order, you can get the zero bias anomaly. Right? Just some people didn't pay attention to it and still continue to work. Now, there are other features. For example, majoranas always appear in pairs. So then you should also look for the correlations. But even that is not unique. So for example, in the setup which I have shown with the wires, you will always have Andreev bound states, and they can also talk to each other. And then it's also not completely clear that this is unique. But you know, there are more and more kind of steps you can try to see, and maybe you asymptotically approach the answer, but it's not written on the particle.